Right, let's make a start. So, thanks everyone for coming along tonight. I know there's other television delights everyone could look forward to later on, but let's crack on with this. So as Phil says, we're here tonight to talk about how astronomers estimate distances in space. We often hear about light years and parsecs and edge of the universe, things like that. But how do we know just how far away these things are? So we're going to take in a bit of a journey. We're going to start pretty close to home and way back in time. And we'll build up what's known as the cosmic distance ladder, because as you'll see along this presentation, each step on the ladder as you go further and further out is really dependent on the certainty with which the previous step has been made and how confident we are in that method of measurement. So first thing we'll start with really is what's a reasonable thing which people could have started to estimate, and that's the size of the Earth. And believe it or not, we've known with quite a degree of accuracy the size of the Earth for thousands of years now. And I think most people, if they had to start from first principles today and you ask them how would you go about determining the size of the Earth, wouldn't be immediately obvious to them. But one of the first people to come up with a really good estimate was Eratosthenes. Now, he was Greek, but he actually lived in Alexandria up in northern Egypt. And he was a learned individual, and he corresponded with a lot of people. And one of the people he corresponded with was someone who lived down in Syene. It's now down this part of Egypt near the Aswan Dam, further up the Nile. But this person noted that on the 21st of June of each year, the longest day of the year, the sun, when it was shining overhead at noon, it shone directly down the well in the center of that town, and you can see all the way to the bottom. And this person noted that it was only one day of the year when that occurred. On any other day of the year, the sun wasn't quite overhead; it was a bit further south, and it didn't shine right down to the bottom. And most people have gone, yeah, okay, it's kind of interesting, and wouldn't have done much about that. But Eratosthenes thought about this, and he noted that up in Alexandria, on the same date at noon, the sun didn't shine down to the bottom of a well in that town. And he realized that this was due to the curvature of the Earth and the fact that there was Alexandria was much further north. And he used that information to figure out the size of the Earth. And the way he did it was like this. I've replaced a well with a tower, just to make it easier. So down at Syene, on the longest day of the year, sun's overhead. The sun's rays would be coming down vertically, and that tower wouldn't cast a shadow. However, up in Alexandria, the sun's at a slight angle, and this tower will cast a shadow. And so what he did was actually measure the angle of that shadow, and he measured it to be 7 degrees. And then he needed to know what was the distance between Alexandria and Syene. So, legend has it that he paid someone to go on and pace it out. In reality, Alexandria was a very extensive trading hub because it was right on the Mediterranean coast. And it's more likely that he spoke to local merchants and estimated from them how long it would typically take to travel from Alexandria to Syene, made some estimates about average travel speed, and come up with an estimate then of the distance. And the calculation he then did was very, very simple. If you assume it's a 7-degree angle down at the center of the Earth, corresponds with that 7-degree shadow. 7 degrees corresponds with this distance here. So take that distance, divide it by 7, and multiply it by 360. And that should be the circumference of the Earth. So that's the calculation he did. Came up with a value of 7,896 miles. If you take the circumference divided by pi, you get the diameter. And that was within 1% of the modern accepted value. So not bad for actually taking an observation that somebody has made and and running with it, running with the idea, extrapolating it from it, seeing what you can work out. So I think that particular story is quite well known. The next piece of the puzzle, though, not quite so well known. And I was certainly taken aback when I first learned about it as I was researching this talk when I first did it. How might you go about measuring the distance to the moon? So again, it was the Greeks. Aristarchus, amongst a number of other people, came up with the general principles, which ultimately led to quite an accurate result. So the way to think about this to begin with is if you hold something up to the sun, like a coin, okay, you have to hold it a certain distance away from your eye in order to only just cover the disk of the sun, okay? And if you measure that distance, it turns out the distance from the coin to your eye is 108 times the diameter of the coin. So if you held something that was 1 centimeter in diameter, you'd have to hold it 108 centimeters away in order to cover up the sun. If it was something the size of a football, let's call it 30 centimeters, you'd have to hold it just over 3 meters away to cover up the disk of the sun. And the Greeks realized this. This was something that they could measure very easily. You just take the diameter, measure the distance, and it always works out at 108 times the diameter. And so they surmised, therefore, that the Earth itself must be casting a shadow out into space that is 108 times the Earth's diameter. Now then, keep that thought. We know that the moon goes around the Earth. That's been known since ancient times. And we also know that on occasion, the moon passes into the Earth's shadow and you have a lunar eclipse. And you can see here a lunar eclipse in progress, and you can see that sort of curved shadow of the Earth as the moon passes into the Earth's shadow. And that's just for comparison, that's the difference between what's going on during a lunar eclipse. You get this curve here, and the moon when it's at first quarter, and you can see it's quite a straight line here. Okay, so that's how you can tell there's a difference between just the moon going through its normal phases and the moon going into an eclipse. So here's what they did. They looked at that curve on the face of the moon as it goes into an eclipse, and they estimated how big the Earth's shadow must be, what the diameter of that Earth, that conical Earth shadow extending into space, how big that must be on the surface of the moon at the moon's distance. Okay, and this is quite. It's very difficult to get an accurate figure, but they sort of surmised that the diameter here of the shadow must be about 2.5 times the moon's diameter. Okay, so far so good. What you can then do on a schematic diagram is say that, okay, the diameter of the Earth's shadow here is 2.5 times the moon's diameter at the distance of the moon's orbit. But here's the problem. You don't know if the moon is quite big and quite close. Again, this distance here is 2.5 times that diameter. Or if the moon's quite small and quite far away. Again, this distance here is 2.5 times the moon's diameter. So you're kind of stuck. You're not much further forward until you factor in something else. I know some of you have been off on foreign climes and I've seen solar eclipses. I think Jason saw one down in Libya a few years ago. And the Greeks, of course, knew about solar eclipses too. And they knew that when you saw a solar eclipse, it was only a very, very narrow strip of land on the surface of the Earth where that solar eclipse was visible. A bit further north, a bit further south, you didn't see a total solar eclipse. You saw a partial solar eclipse. And from that information, they realized that the moon's shadow must only just touch the surface of the Earth. If the moon was any closer, you'd see it over a much larger region of the Earth's surface. So they took that knowledge and combined it with what I talked about earlier about the Earth's shadow, and they were able to come up with a pretty accurate estimate for the distance to the moon. And here's how they did it. So I've got to do some maneuvering here. I'm going to take this shadow. I'm going to switch it around. So all I've done here is take that, kept it at the same scale, and switched it around like here. So this isn't a true astronomical representation. All I've done is take that shadow and put it here. Okay, now what do we know about this? Well, we know that these are spherical objects. We know that their shadow length is 108 times the diameter. And we know that the Earth's shadow at the moon's distance is 2.5 times the moon's diameter. Okay. You can also see that these are similar triangles. Okay. The cone angle is the same. Okay. We know the relationship between that and that. That distance there is 2.5 times this distance. Okay. So therefore, because they're similar triangles, this distance here must be 2.5 times that distance. Okay. And this distance here is the moon's orbital distance. Okay. So this must be 3.5 times the moon's orbital distance because they're similar triangles. This is 1 Earth-Moon distance. This is 2.5 Earth-Moon distances. So the total is 2.5 plus 1 is 3.5. So what you can do now is, you know the size of the Earth. You know that cast a shadow that's 108 times the length, the diameter of the Earth. I do know that equates to 3.5 Earth-Moon distances. So what you do, take the Earth's diameter, multiply it by 108, and divide it by 3.5. And that'll give you the Earth-Moon distance. And that's what the Greeks did. They came up with an estimated value of 240,000 miles, which again, within 1% of the modern accepted value. Now, I think that's absolutely outstanding in terms of a thought experiment about how to solve this problem and to come up with a solution like that. I'm astounded at just how intelligent those people were back then. Any questions on that? No.
I can just say I've shared your astonishment, William. I think it's just I marvel at it.
Mm-hmm.
I marvel at both of the first 2 steps on your cosmic distance ladder.
Yes, it's amazing what you can do when you don't have a distraction of television. When you have to sit and think about things. So yeah.
Very good, very good. Thank you.
Okay, right. So we've now got our local backyard kind of measured. We've got some reasonable estimates. Of course, these days we know the distance from the Earth to the Moon very, very accurately. Back in the late 60s, early 70s, there were a series of Apollo missions. There's now a total of 3 lunar reflectors from the Apollo missions on the surface of the Moon. Here's one of them from Apollo 11. They very unhealthily left the plastic dust cover discarded off to one side. And these are very much like the corner cube reflectors you have on bicycle pedals and things like that, or the back of cars, where you shine a headlight on it and the light gets shone, reflected directly back at you. And the idea here is that you take a laser on the Earth, you bounce it off these reflectors on the surface of the Moon, and you time how long it takes that pulse of light to get from the Earth to the Moon and back again. And from that, you can derive a very accurate estimate of the distance to the Moon. Okay, so we know it to an axis of better than 10 millimeters, and indeed we now know that the Moon is slowly spiraling away from the Earth at a rate of about 38 millimeters per year. And just coincidentally, that's about the same rate as human fingernails glow. So next time you chew your nails or clip your nails or whatever you do, have a look at the pieces that are left over, and that's how much the average distance from the Earth to the Moon is increased since you last cut your fingernails. So something to muse about next time you're doing that. Okay. Earth-Sun distance, how might we go about calculating that? Well, this is a bit more of a challenge. Again, the Greeks had a go. They, again, had a thought experiment that, well, if we look at the Moon at first quarter, We know that there's an angle of 90 degrees between the Earth, the Moon, and the Sun. That's where the Moon is at first quarter. But the Sun must be at something slightly less than 90 degrees. Okay, so if we measure that, we'll have a very tall, skinny, right-angled triangle. So perhaps we can measure that. Of course, the challenge is that in order to see the Sun and the first quarter Moon simultaneously, the Sun quite often, in order for the sky to be dark enough that you can actually see the first quarter Moon, quite often the Sun's quite low and you get atmospheric reflection effects, which alter the apparent position. The apparent position of the Sun is different from its true position, and so there's a lot of uncertainties in this angle, and they were never, with that method, really able to come up with a close approximation. They knew that the Sun must have been very, very far away compared to the Earth-Moon distance, but as you can appreciate, a very small error in this angle would lead to a very large error in this distance here. So that was a bit beyond the technical capabilities of the Greeks back in their day, and it took a bit more effort later on to sort that. I've sort of abbreviated this talk a little bit in the interest of time, but one of the techniques was to observe transits of Venus. I do have memories, Phil, of our attempt at observing Venus back at Jackson's boat back in 2004, was it? I can't remember.
2003 or 4, yes.
Yeah, it was something like that, yeah. So this is when Captain Cook went on his famous voyage on Endeavour. The idea was to observe transits of Venus from different locations on the surface of the Earth and use accurate timings from those different places, because the effective parallax would have Venus beginning to cross the disk of the Sun at different points of time on different points of the Earth's surface. And by accurately measuring that, they might be able to, again, triangulate the distance to the Sun. Unfortunately, the infamous black drop effect put paid to that. There's quite a lot of uncertainty in terms of when Venus genuinely did fully cross the disk of the Sun, or the edge of the Sun. So there's quite a lot of error in those timing measurements. So again, the results were inconclusive. And ultimately, it came down to parallax measurements of asteroids, which ultimately determined the distance from the Earth to the Moon. Okay, and just speaking of asteroids, I know you gave the night sky talk earlier, but if you just Google Vesta, Vesta is well placed in Leo at the moment. So if you got some binoculars, go ahead and have a look in the sort of the haunches of Leo, not the head, but the other end of it. If you just Google it, you should be able to track that from night to night. Vesta is moving pretty quickly through Leo at the moment. Okay, let's move on to this gentleman, Tycho Brahe. He's essentially the last of the great astronomers who operated in the Flea telescopic era. Again, another interesting person to look up on Wikipedia. At one time, the richest man in Denmark. He lived in a castle, kept a pet moose. The moose came to an unfortunate end after getting drunk and falling down some stairs, but that's another story. Famous too for having a gold nose, because he lost his in a duel. Okay, he was mentioned that he was a great observer, and he specialized in particular in making positional measurements of the planets. And they would do this by eye and compare the positions of the planets against the background stars, and kept very meticulous records. And when he died, those records came into the possession of Johannes Kepler. Johannes Kepler was a very gifted mathematician, and he was able to derive from those observations mathematical laws governing the movement of the planets around the Sun. And they're known as Kepler's 3 laws of planetary motion. I can sort of summarize them here. The first is that planets move in ellipses as opposed to circles. The Sun is at the focus of one of those ellipses. The other one is empty. He also derived that planets sweep, it's called, they sweep equal area in equal time. So if you drew a a line from the sun to a position of a planet, and then back to onto another planet and back to here, that area that would be swept out is the same for an equal amount of time. And the upshot of that really is that as planets are closer to the sun, they move faster. And when they're more distant from the sun, they move more slowly. And you can sort of see that with this red halo. When the planet's close to the sun, that halo is longer because it's moving faster. And when it's at the furthest from the sun, the halo is quite short. It's moving more slowly. So it derived these three laws of planetary motion. And from that, he's able to work out that the radius of the orbit, the average radius, the cube of that is directly proportional to the square of the orbital period. So a good analogy there might be Jupiter, where Jupiter is about 5 astronomical units from the sun. If you take 5 and you cube it, you come up to about 125. Take the square root of that, it works out about just over 11, and the orbital period of Jupiter is about 11 years. So r cubed over t squared is a constant. So he's able to derive all that, but it was a relative measure. Okay, you could sort of say that Jupiter must be 5 times further away from the sun than the Earth is. But at that time, they didn't know the Earth-Moon or the Earth-Sun distance. She couldn't say how many miles away Jupiter was. You could just say it was 5 times further away from the sun than the Earth was. Okay. I've mentioned Captain Cook and the transit of Venus. Okay, and the infamous black dollop effect. Okay, we'll move on now to this gentleman, Ole Lomer. The reason I'm mentioning him is because he was the first to come up with an accurate estimate for the speed of light. And the reason I'm bringing this in is that, you know, as we move further and further out into space, using miles and kilometers and whatever becomes much too cumbersome. The numbers just get far, far too big. So the way he did this calculation was that he was observing the appearance and disappearance of the moons of Jupiter. And he noted that when the Earth and Jupiter were on the same side of the sun, the eclipses tended to happen on schedule, because, you know, people were able to come up with calculations which determined, based on Kepler's laws, when these moons should pass behind the disk of Jupiter or pass in front of the disk of Jupiter. But he noticed that at other times, when the Earth was on the opposite side of the sun from Jupiter, that the time estimates were right. These things seem to be happening late. And what he realized was that it was a difference in the light travel time. Okay, if the Earth had been here, you'd see it at a certain time, but because the Earth's over here, that light from the moon that's just about to disappear behind the disk of Jupiter has to travel across the distance almost of Earth's orbit. And using that information, he was able to come up with the first truly accurate estimate for the speed of light. And it works out, you know, the modern value is about 186,282 miles per second. So just to put that in context, most people would drive about, I don't know, 12,000 miles a year. So, you know, light travels further in 1 second than most people would do in 15 years of modeling. So it's quite speedy. Okay. Now that we've established about, you know, light travel time, we'll move back to measuring distances. We'll come to this gentleman, Frenchman, Friedrich Bessel. And he's famous for working out the first accurate estimate of a distance to a star other than our sun. Okay, and he used the principle of parallax. So I'm sure you're all familiar with it. If you hold a finger out in front of your face and close one eye and line your finger up with something like a window or the side of the TV or computer screen or whatever, and then you know, close that eye, open your other eye, and the position of your finger relative to the background changes. You can sort of flick that back and forth. And that's simply because you're looking at that same object from 2 different positions. So he used that principle, but instead of using his eyes, he used the actual distance of the the Earth's orbit. Okay, and he would measure the position of a star against background stars, let's say in January, and then repeat that observation in July, and you could see that the position of a star against the background stars appeared to change. Okay, and using that technique, he was able to come up with the first estimate of the distance to a star, and that works reasonably well. It'll work out to a few tens of light years. After that, the angles become so small that it's very, very difficult to measure them from the surface of the Earth. The reason being this. I think anyone who's looked through a telescope, this is a telescopic view of the moon, and you can see how the image is shimmering there. And this is down to seeing in the atmosphere, essentially turbulence in the Earth's atmosphere. And so when you're trying to make a very, very small angular measurement on the night sky, the Earth's atmosphere becomes a limiting factor. You just can't get an accurate enough measure. So we'll then have to wait for the space age. Okay. And there's been a couple of missions dedicated to this, both European missions. The first one is Hipparchus. That was doing its work between 1989 and 1993. And because it was up above the Earth's atmosphere, it was actually supposed to be in a geostationary orbit going around the Earth. And the same sort of orbit as communication satellites. However, the boost motor failed and it got stuck in a transfer orbit. So they were able to rescue most of the science from it. They needed a few more ground stations, but they got some pretty good data from it. And again, using that technique of measuring the positions of stars at one point in time and then measuring them again 6 months later, able to get very, very accurate angular positions. That extended the range of this parallax technique out to a few hundred light years. There's been a successor, and it's still operating, the Gaia mission, which is shown down here. Again, it's another European mission. That was launched back in 2013, and it's still operating. I think currently scheduled to end next year, but if it's still got enough capability, they might extend that mission further. That's going to measure around about 1 billion celestial objects. Each one's going to be measured at least 70 times. So you're getting a lot of good data there. To give you an idea of the precision of this satellite, it's going to be able to measure, well, it could differentiate between the left hand and right hand thickness of a human hair at a distance of 1,000 kilometers. So we're talking micro arc seconds here in terms of positional accuracy in the sky. And using that, it's going to get out to quite a few hundred light years in terms of an accuracy of 1%. In fact, it's going to be able to measure around about 30,000 light years distant. So that takes us right into the center of our galaxy. Stars out at that distance, they estimate that the accuracy of those distances will be around about 10%. So extremely high precision instrument, and lots of data flowing from that now, and that's helping astronomers in all sorts of ways, not just mapping the local galaxy, but also helping in other aspects in terms of proper motion across the sky. As we know, the stars are orbiting the center of our galaxy, but they're not all orbiting in exactly the same orbits, and so their position relative to each other is going to change over time. So we can accurately measure that. And Phil mentioned my meteor work. I also do asteroid occultation work, where asteroids pass in front of stars, and from that you can determine the size and shape of asteroids. So again, this Gaia data is really helping the asteroid occultation people, because in order to be successful, you really need to know the position in the sky of the stars and the orbital position of those asteroids. So it's helping astronomers in all sorts of ways. Okay. Hopefully these are the sort of characters you don't see too often. Speed policeman. And the technology they use is basically to do with the Doppler effect. I'm sure you're all familiar with the Doppler effect. This is where sound waves are emanating from an object. If the object's stationary, the sound waves are pretty constant pitch. Whereas if the object emitting the sound waves is moving, they get compressed in front of it and spaced out behind it. So this is why it's a classic sort of ambulance. As an ambulance is approaching you, the pitch of the siren appears to go up. And then as it's receding from you, it appears to go down. I'm sure you're all familiar with that. So exactly the same thing happens with light. And if you look at a spectrum of light, you take a light and you split it up through a prism or through a diffraction grating, and you look at it really, really closely, you'll see what are known as Fraunhofer lines. These are dark bands in the spectrum. And these are down to particular quantum changes in the electron positions within atoms in the intervening gas. So if an electron jumps from a lower orbit to a higher orbit, that could be because it's absorbing a very specific wavelength of light. And if that wavelength of light is absorbed, then you get this dark band because that's being absorbed. The adjacent wavelengths are still getting through to the observer. So you get these absorption lines appearing in a spectrum. And each of those absorption lines are very characteristic to the element which is present and has been absorbing those. So it acts like a chemical fingerprint. So the absorption lines for sodium are very different from those for helium or oxygen or argon or things like that. Okay, so how does that help us? Well, if you take a distant object, and this is the Cloud Nebula. This is a supernova which exploded, well, it was observed to explode back in 1054. And if you look at that object through a spectrograph, the gases in this shell, this expanding shell, are moving towards us. And what you see then is those spectral lines, due to the Doppler effect, are shifted. They're not really where they should be on the spectrum. They're moving. And that's because the gas shell that's emitting this light is moving towards us. So it's a bit like the siren on an ambulance. It's coming towards us. And so the pitch is higher than it otherwise would be, and these lines appear out of position. And if you measure what that shift is, in this case, it would be the blue shift. They're moving to a higher frequency because the front face of this is moving towards us. You can work out the speed with which that shell is expanding towards us. So you can combine that data with modern and old photographs of this nebula. If you go back and look at photographs of the same object from a few decades ago, it is noticeably smaller in terms of angular size on the sky. So by combining that data of how much it's increased in angular size and the speed with which the front face of that gas shell is coming towards us, you can actually calculate how far away the Cloud Nebula is from us. And that's the primary method by which we're able to determine the distance to that object. And we can do that with other types of expanding objects like that. There's many other supernova elements in the sky. Okay, so that takes us maybe we've gone out a few hundred light years now. Okay, but that's not very far. Our galaxy we know today is about 100,000 light years across. So how do we know that kind of information? Let's consider for a moment, let's say a cruise ship. Let's say you're standing on a beach, you're looking at a cruise ship. And that cruise ship, let's say, is maybe, I don't know, 4 miles away, something like that. Now, there might be people on this side of the deck, the side of the deck facing towards us, and there might be some people on the far side of the ship, on the other side of the deck. So some people will be slightly under 4 miles away from us. Some people will be slightly more than 4 miles away from us, okay? But in general, you would say they're 4 miles away from us, okay? Just hold that thought for a moment. If we then look at objects out in space, which we know aren't at a fixed distance from us. These are the large and small Magellanic Clouds. We know that those are roughly spherical in shape, and some parts of the Magellanic Cloud will be closer to us than other parts of the Magellanic Cloud. But in general, the Magellanic Cloud's at kind of a fixed distance from us, okay? So again, hold that thought, and let's think about this lady here. Not very well known, unfortunately, but this lady really did absolutely and utterly revolutionize astronomy, because she discovered something which is in very widespread use, and has been for, getting on for nearly 200 years now. So she discovered a relationship with regards to what are known as Cepheid variables. So Cepheid variables are pulsating stars. They're stars that change their brightness. Sometimes they're bright, sometimes they're a bit fainter. And her job, she was part of Edwin Hubble's group. Her job was to study photographic plates of the night sky and look for these Cepheid variables. And it really is painstaking work. This is a Hubble Space Telescope image, and this is a Cepheid variable here. And you can see on this flame here, it's quite faint. It's a bit brighter here and relatively bright here. And this is laborious, painstaking work. You're comparing photographic plates. You're not doing this in a computer. And you're switching back and forth between images, back and forth, looking for things that are in the same position but are changing brightness. And that was her job. So she found lots of these, which is great. But she also noticed something else. She noticed that the difference between the faintest and the brightest in terms of the time period, okay, the larger the amplitude in change of brightness, the longer it was between the bright period and the short period. So that cyclic period was longer. And this next graphic kind of shows you here that for, the longer the period, the greater the change in absolute magnitude. Now, that is useful because if you can establish a distance to a Cepheid variable using the parallax method, and you know its true distance, and you know its period, let's say it's 60 days, you can work out its absolute magnitude, how bright it would appear at a given distance of 100 light years. Okay? If you then have that information and you look at a Cepheid variable, a much more distant object, let's say in the Andromeda Galaxy, and you compare its apparent magnitude, how bright it appears compared to its absolute magnitude, you can work out how far away it is. It's a little bit like if you had a 100-watt light bulb. So you know it's a 100-watt light bulb, okay? If it's quite close to you, it appears very, very bright. If you put it half a mile away, you can still see it, but it's much, much fainter. But you still know it's a 100-watt light bulb. So by measuring how bright it appears to be, you can actually work out how far away it is. And it's the same with these Cepheid variables. By measuring their period, you can work out whether, essentially, are they a 100-watt light bulb, a 40-watt light bulb, or a 60-watt light bulb? And once you know that, measure their apparent magnitude, and then you can work out how far away those objects are. And that technique was used to establish the distance to the Andromeda Galaxy. I'm sure you've seen the Andromeda Galaxy. If you're on the dark side, you can see it with the naked eye through binoculars, or I'm sure some of the imagers that Phil was mentioning earlier, I'm sure they've taken photographs of it. Spectacular object, much bigger in reality in the sky than the naked eye observations would suggest. If we could see it like this is about 3 moon diameters across. Okay, it's a pretty large object in the sky. Okay, something to remember here. There's typically about 100,000 million stars in a galaxy. Some are bigger, some are smaller, but on average about 100,000 million. Just keep that number in the back of your mind for a moment. Any questions so far?
There's none appeared in the chat, William. I just think it's I'm enjoying this journey.
Okay.
You're taking us further and further away, and it gets more and more. I would say more and more complicated, not necessarily more and more impressive, because some of the early measurements were very impressive. But
yeah, again, it's some people would have looked at C-feed variables and gone, yeah, they're interesting. But taking that bit of information and doing, peeling back another layer of onion, digging with it a little bit more. What else can I extract from this? And it wasn't a professional astronomer. It was someone who's employed to switch between photographic plates. And that person had the diligence to say, this plate was taken on that date. That plate was taken on this other date. Those two, this one's varying quite a lot in brightness. Those ones not so much. And essentially drawing that graph. Okay.
You're taking me back through my GCSE in astronomy. I think Carolyn would like to ask you a question.
Okay.
Yeah, you showed these photographs that she sort of worked on, but there was another star just below left, about 8 o'clock, that also seemed to vary in brightness. It's
yes, here.
Brightest, that one, yes.
Yeah.
Is that just pixelation or something?
No, I think that's another one. There's another C-feed variable in this field of view. Remember, we're looking at a distant galaxy. In this case, I think it's M100. So even with the Hubble Space Telescope zoomed in on a very small part of the sky, there are hundreds, if not thousands, of stars in this field of view. So yes, it's not surprising that there's more than one C-feed variable in the sequence of images. But yeah, that's a good spot.
That's okay.
I hadn't noticed that before.
But the plates that Henrietta was working with were far less detailed.
Oh, absolutely right. This is a modern digital photograph. Henrietta would have been working on literally glass plates coated with photographic emulsion. You had to treat them very, very delicately. And I say these days it's very easy on a computer to flick between images and look for differences. But this is, you have to look at one plate and then, move your head, look through a different eyepiece at another plate, remember what you saw on the first time round, and move your head constantly back and forth. That would not have been easy work.
Very, very, very astonishingly impressive.
Absolutely. And unfortunately, very few people know her name.
Thank you.
Okay.
Can I just say something else about using photographic images versus computer images? Is that the resolution is usually much finer and you can enlarge them ever so much more than you can a computer image, even I expect a Hubble image. I mean, I've found this since my work has gone digital compared to the old photographic system. And I cannot enlarge anything like as clearly. So
yeah.
Fine emulsion is amazing material.
You're absolutely right. And, modern digital cameras, they got more and more and more pixels on them. But I think a great example of this was at least landing of the Perseverance rover on Mars, where they've got super HD cameras. But the limiting factor these days is not the resolution of the camera; it's the bandwidth with which you can transmit that data. And quite often with these space missions, they have to either highly compress or throw away some of the data in order to get some sort of image down from the satellite down to Earth. If you sent it down at full high resolution, it would take a very long time just to download one image. But yeah, you're absolutely right. That's until we figure out ways of rapidly communicating large amounts of data over very large distances in space, out to low Earth orbit or high Earth orbit, or the distance of Mars. I think we're going to be restricted to having relatively low resolution images compared to what would have been a photographic plate from the past. And it's the same when you're downloading images off the internet as well. It can be quite time consuming to download the original native very high resolution image. Okay.
Yeah, thank you.
Right, let's move on. This is an artist's impression of a binary star system. And what we've got is a star here, and we've got a white dwarf companion star. Okay, and they're in very close orbit with each other. And what's happening is the gravitational field of the white dwarf is actually pulling away some of the outer layers of the star and forming a accretion disk around the white dwarf and slowly falling down onto the surface. Okay. And given enough time, this is what's going to lead to a supernova explosion. In particular, what's known as a type 1a supernova explosion. So I'll give you an analogy here. Suppose you had a pint glass, and at the top of the pint glass, you tipped on a birthday candle, okay? And you'd lit the birthday candle, okay? So the flame's just at the very lip of the glass, and you started to pour gunpowder into the pint glass, okay? There comes a point in time when the pint glass is full, and the birthday candle is going to ignite the gunpowder, and you're going to get an explosion, okay? Now, it doesn't matter whether you pour that gunpowder in very, very slowly or very, very quickly. At some point, the pint glass is going to be full, and it's going to explode. And because you've always got the same volume of explosive material, you're always going to get the same size bang. Okay. And it's the same sort of thing going on here with these accretion disks around white dwarfs. Okay. At some point, enough material falls on here where you reach a critical limit known as the Chandrasekhar limit. And so at 1.44 solar masses. So once this reaches a mass of about 1.44 times the mass of the sun, it's going to go bang and become this type 1a supernova. Now, that's quite useful to know, because if it's always the same size bang, it's generally speaking always going to give out the same amount of light. So as an astronomer, what you can do is look out for these types of supernova. And you can distinguish these supernova from other types of supernova, like the classic type 2 core collapse supernova, when a massive star reaches the end of its life and runs out of hydrogen at its core and collapses in itself. They've got a very different spectral signature. If you look at them through a spectrograph, their light curve is very different from a type 1a supernova. So you can't differentiate between them. Now, I mentioned that these are always the same size of explosion, and hence they give off the same amount of light. So if you look at a distant galaxy for these type 1a supernova, and you measure the apparent magnitude, the further away they are, the fainter they're going to be, because the lights let's have a longer distance and to split out more. So a galaxy that's close by with one of these supernova going off is going to be brighter than a similar galaxy much further away with one of these supernova going off, simply because, you know, the further one away, the lights split out a lot more. So again, it's that sort of 100-watt light bulb versus 40-watt light bulb analogy. So using that technique, we can start to measure the distance out to galaxies of a few 100 million light years. The Andromeda galaxy is about 2.2 million light years away. Anything, you know, much further out than that, you can't really use Seaford variables anymore. So you need to use a different technique. And this technique of using type 1a supernova is something that gives you a much greater range. You can look out much further. Okay, and using that technique, as I say, we can go out to a distance of a few hundred light years. Sorry, a few 100 million light years, I should say. Apologies for that. Okay, next up, another gentleman that very few people have heard of. This gentleman, Vesto Slipher. It's part of Edwin Hubble's organization, okay? Now, this guy made a very important observation, which was picked up on by his boss, and his boss sort of developed it a bit further. But ultimately, what Vesto Slipher noticed was that when he looked at distant galaxies through a large telescope, this is Hubble himself, and he took a spectrum of them, okay? And he noticed that the spectral lines were in the wrong place. They were, in this case, lead shifted. So they've been shifted towards the lead end of the spectrum. And that indicated that those galaxies were moving away from us. And it didn't matter where in the sky he pointed at his telescope and looked at these distant galaxies, they all appeared to be moving away from us. Now, the natural thing to think there might be, well, maybe the Earth's at the center of the universe, and the universe is getting bigger, and everyone's moving away from us. But Edwin Hubble took a little bit more time looking at the data and realized it was a relationship. The further away the galaxies were from us, and you could tell that from the supernova data and the Cepheid variable data, the faster they were moving away from us. And the explanation is pretty straightforward. I want you to imagine for a moment you got something like a scone with some flute in it, okay? So let's say this is when you first form it into the dough, okay? But you haven't put it in the oven yet. It's just sitting there on your table, ready to go into the oven. But before you put it in, you measure the distances between, let's say it's pieces of flute. Let's say it's currents or layers and something like that. You measure the distance between them, yeah? And we've got 30, 40, and 50 millimeters there, okay? You then put it into the oven, and it gets bigger. Let's say it doubles in size. So the spacing that was 30 millimeters now becomes 60. That was 40 millimeters now becomes 80. That was 100 millimeters now becomes, that was 50 millimeters now becomes 100 millimeters, okay? So it's essentially doubled in size, let's say in the space of an hour, okay? So what you can then say is that, well, if that's gone from 30 to 60, it's moved, or the distance between the two is increased 30 millimeters per hour. This one that was 40 is now 80. Well, it must have moved it 40 millimeters per hour. And this one that was 50 millimeters away and is now 100 millimeters away, it must have moved it 50 millimeters per hour. So in short, the further away it was to begin with, when it's doubled in size, the faster it's moved away from us. Okay? Now, the thing to bear in mind here is that the currents haven't moved through the dough. Okay? The dough itself has got bigger. And it's the same sort of principle in space. The space between galaxies has got bigger. It's not like the galaxies themselves are wishing apart from each other. It's simply that the space between the galaxies has increased over time. And it wouldn't really matter which current you started on and you repeated this experiment, you come up with the same result. No matter which one you were on, the further away they were to begin with, the faster they're moving away from you. And that's the realization that Edwin Hubble had. And we now all know about the expansion of the universe. So how's that technique useful to us? Well, what you can do is you can measure the redshift of distant galaxies. And if you've got the next rung underneath, for example, type 1a supernova data, okay, to give you a measure about how far away it is, and then you look at its redshift, again, by measuring lots of these and building a good statistical model, you can then build up a law or a rule. It's known as Hubble's law that gives you a relationship between the redshift of a galaxy and how far away it is. Okay. And Hubble's law is currently, I think Hubble's measured at, the Hubble Space Telescope's measured to something like 73.6 kilometers per second per megaparsec. So that's how quickly the universe is expanding. I do remember many years ago at university, the Hubble Space Telescope hadn't been launched, and there was two figures in play. There was one study that said it was 50 kilometers per second per megaparsec. Another one said it was 100. And my physics teacher always said, use the 100 figure, makes the maths a lot easier. But now, we've got a more accurate figure. That was a primary reason for launching the Hubble Space Telescope in the first place, was to get a really accurate measure by measuring the distance to lots of distant galaxies, looking for those Cepheid variables in them for the nearby ones, looking for type 1a supernova in the more distant ones, benchmarking those lower rungs in the ladder in order to get a good measure of the Hubble constant. And so you can now map out distant galaxies out in space. This diagram sort of bow tie shaped. Reason being that we have to look above our galactic plane and below our galactic plane. We can't really look very well along our galactic plane because there's lots of intervening gas and dust blocking our view of distant galaxies. So that's why we can sort of only look in really two directions out into the universe, because our own local galaxy kind of gets in the way. And you can start to see here some interesting patterns. It's not all homogeneous. You can see some sort of bubbles and voids here, okay? Each blue dot here represents a galaxy. And what you start to see here is some of the underlying structure of the universe at very large scales. Things aren't evenly distributed. You get these sort of, as I say, it's almost like a sponge where you have these voids where there's not very much in it. And then you have these regions, a bit like the actual sponge material, where galaxies tend to clump together. So that's quite an interesting effect there, which no one was expecting. Just another plot. Again, this is projected on galactic longitude. Not many observations along our galactic plane, again, because the gas and dust is getting in the way. But again, you can see these sort of lumps, that there's a lot of galaxies here, not so many here. Okay. Okay, let's keep moving. Hubble Space Telescope. Again, I've talked about the primary reason why that's been launched. But when you're in charge of the Hubble Space Telescope, there's some perks to be had. The person in charge is called the director of the Hubble Space Telescope Institute. And he heads up a committee which is essentially responsible for sifting through all the applications people make for getting observing time on the Hubble Space Telescope. It's an expensive instrument. It's very popular. Lots of people want to use it, and demand for its supply. And so that committee sifts through all the requests and says, yeah, we'll allow this person, an hour's observing on the Hubble Space Telescope for that particular thing they want to look at. But all these other people, I'm sorry, their application isn't good enough. Well, they can maybe use a different telescope. Now, one of the advantages of being in charge of that committee is that you get some observing time of your own. Back when the Hubble Space Telescope was first launched, that equated to about 10%. So about 10% of the time available for observing the Hubble Space Telescope. The director of the institute at this time was a guy called Robert Williams. He could decide himself. He didn't have to go through a committee. And so he wanted to do a particular experiment. He wanted to observe empty space. He thought, I wonder what would happen if we pointed the Hubble Space Telescope at a part of the sky where ground-based telescopes couldn't see anything. There are no stars, there are no galaxies, nothing at all. What's out there? So he saved up each of these increments he had of available time, and he decided to splurge them all in one go. And it equated to about, probably getting on for about a week's worth of time on the Hubble Space Telescope. It wasn't all done in 1 week. He took a few tens of hours on one occasion, a few tens of hours on another occasion, and then they combined the results. The part of the sky they chose was actually in the Big Dipper, just around about this region here. And the reason they chose that part of the sky was, again, it's up and away out from the galactic plane. Okay, so you're not going to get any intervening gas and dust or stars from our own galaxy, and our best ground-based observations suggested that there's nothing there. So that's the region they chose. A little tiny part in the sky. Just to give you an idea of the sense of size on the sky, I want you to imagine a tennis ball. And imagine you've got that tennis ball and you set it on the goalpost on a football pitch. And then you start walking the length of the football pitch back to the other goal at the other end of the football pitch, 100 yards away. And when you get to that other goal, look back at that tennis ball that's perched on top of the other goal at the other end of the pitch. And that tennis ball will be blocking out a little tiny part of the sky. That's essentially the size, the area of the sky that the Hubble Space Telescope was looking at. A very, very tiny part of the sky. And here's what they saw when they got the results back down and they combined them. Okay, so ground-based telescope suggesting nothing there, it's completely blank. And you can see here there's thousands of galaxies. Each of these dots of light is not a star, it's a galaxy. And this is called the Hubble Deep Field image. Remember, the light was so faint that ground-based telescopes couldn't detect it, okay? This suggests these objects are very, very far away. Hubble used its spectrometer to measure the redshift of all these galaxies and detected that they were very, very far away. You know, hundreds and hundreds of millions of light years away. In fact, sorry, billions of light years away, I should say. And if you look back, you know, we know now, for example, that the universe is about 13.7 billion years old. Okay, we're looking back about 10 billion years here in this particular image. The universe was a lot younger. Okay, and we see galaxies in various stages of evolution. Now we're used to seeing those sort of glorious sort of elliptical galaxies or spiral galaxies. But here you can see a number of misshapen ones, a bit odd shaped, a bit amorphous, so just blobs in the sky. 10 billion years, the universe was a lot smaller than it is today. Galaxies were a lot closer to each other than they are today. Being a lot closer to each other, they were more akin to gravitationally interact and distort each other. So that's why we see so many galaxies and why they're all weird different shapes. And again, by looking at the redshift of these, we're able to deduce how old they are and hence how far away they are. So we're at about 10 billion light years now. Obviously, there are a number of servicing missions to the Hubble Space Telescope in the intervening years, and higher resolution and more sensitive cameras have been installed. And we've now got the Hubble Deep Field, the Hubble Ultra Deep Field, and then when they upgraded them for the last time, the Hubble Extra Deep Field, I think it's called. Okay, and each time we're looking a little bit further back. We can now look back to essentially within 500 million years of the Big Bang itself. Okay. We can't see anything in these images older than that. They've looked at all of them. They've taken done a spectral analysis of each of them. We can't see anything older than that. And the reason for that is that prior to the galaxies forming, there may have been stars, but they wouldn't have formed yet into galaxies. And prior to that, and they wouldn't be big enough and bright enough to see. And prior to that, stars hadn't formed yet. We're in what was known as the Dark Ages, this region here. Okay, so the Big Bang had occurred. After its 300,000 years, it had expanded and cooled enough that neutral hydrogen could form. We can see the sort of last remnants of that in the cosmic microwave background. But those clouds of neutral hydrogen had not yet collapsed down into stars. Obviously, when that did start to happen, those stars would have shone for a few hundred million years before going supernova, and then distributing their higher, heavier elements out into the universe for next generation stars to form. And you need those heavier elements for longer lived stars to form. And once you've got longer lived stars, you've got longer-lived galaxies, or at least galaxies that have got stars that live long enough to be observed. So let's say the Hubble Ultra Deep Field, we're going out about here. The next one out was going a little bit further, but essentially the limit of our observational capability is typically within 500 million years of the beginning of the universe. So we're going out to about a distance of about 12 and a half, 13 billion light years. We can't see anything beyond that because there's nothing giving out light beyond that. So that gives you an idea of just how far we can see as we measure distances out into space. Okay, how am I doing for time? I'll just start to lap things up. Okay.
We normally keep going till getting on for 9 o'clock, with perhaps by wrapping up by 9 with some questions. So you can keep going for a bit, William.
Okay. Well, I've sort of rattled through this, and maybe you can spend a bit of time just answering questions if you like. I haven't got too many more slides here. Okay. I want you to think about sandy beaches. Hopefully, we'll be able to have a beach holiday soon. I want you to think about all the sandy beaches on the world, and let's make some assumptions here. Let's say that all of the world's coastline is sandy. It's not, but let's make that assumption. And if you measure the world coastline length, and you have to make some assumptions there. We're not going down to fractal levels, but it's about 356,000 kilometers. So if we assume that we had a bar of sand that's 356,000 kilometers long, about 100 meters wide and 10 meters deep, okay? That could be a bit of a rough estimate of how much sand there is on all the beaches of the entire world, okay? So you work at the volume, okay? And it works out about 356 billion cubic meters, okay? We can then look at sand grains and make some assumptions about how big a sand grain is, okay? So it works out about, don't know how many zeros that is, cubic meters. Divide one by the other, and you get an estimate of the number of sand grains on all of the beaches of the whole Earth. And I think that's a 3 followed by 21 zeros. Okay, bit of a rough estimate. Go back to the Hubble Space Telescope Deep Field image, and I don't know if you remember how many stars there are in a typical galaxy. It's about 100,000 million. Okay, and remember I told you the area covered by the field of view of the Hubble Deep Field. I think it's about 1/13 millionth of the night sky. And this image alone contains about 10,000 galaxies. So you can start to estimate how many galaxies there might be in the observable universe. Okay, so 10,000 in that image, that covers 1/13 millionth of the night sky. Divide one by the other, and you get this many galaxies in the universe, about 130,000 million. Okay, multiply one by the other to get an estimate of the number of stars in the universe. Okay, so that's a 13 followed by 21 zeros. So you can see, therefore, that there's more stars in the universe than there are grains of sand on all the beaches on the entire world. And I think that's a pretty sobering thought to give you an idea of the scale and the size of the universe as to what's out there. We've got a lot of ground to cover, a lot to observe, a lot to study, and I think there's plenty to keep our children, our grandchildren, our great-grandchildren busy in astronomy for many, many generations to come. So with that, thanks very much for your time, and happy to field any questions you may have.
Thank you, William. I find these numbers just mind-blowing.
Mm-hmm.
I'd like to ask some questions when you've still got your slides accessible to you. Maybe sure. others would as well.
Sure.
You showed a slide with the Hubble Space Telescope at the middle of, not very far back.
Yeah.
The middle of the universe.
Yes. Let's just this one here. Yeah.
That one, yeah.
Mm-hmm.
So, this concept baffles me endlessly. So the edge of the observable universe is 13.7 billion or 14
light years away.
Light years away from where we are.
Mm-hmm.
And if you were at the extremity of that, looking from there, would it still be 13.7 billion light years away in the continuing direction?
Yes. It's when you see on TV, for example, animations of what the Big Bang might look like, what you tend to see is, a dark loom and some sort of explosion going off in the middle of it, and things flying outwards, and that presumes that the universe is expanding into something, is expanding into a pre-existing space, and that's and I understand why TV producers do that sort of thing. They need to show something on screen, but there is no center to the universe.
You could be led to believe that the way you've drawn that, the Hubble Space Telescope is at the center of the universe, which
understood.
Plainly it isn't.
Yeah. Imagine it a little bit if we try it on the surface of the Earth, okay? You're standing somewhere on the surface of the Earth, you can see as far as your horizon. And that might be, depending on how tall you are, that might be 4 or 5 miles away, yeah?
Yep.
You could walk to another part of the surface of the Earth and you can see different stuff, but your horizon's still 4 or 5 miles away. Okay, so no matter where you go, you can only see to a certain horizon. And the thing about, the better way to think about this is, if I look in one direction with a telescope, and I can see out as far as 13 billion years, yeah? If I turn my telescope through 180 degrees and look in the opposite direction, I can see out 13 billion years. Okay?
Yep.
Here's the question. And again, they've done this with the Hubble Ultra Deep Field. If you do that experiment and look in opposite directions, the view you get is pretty much the same. They're not the same galaxies, but the size and shape and distribution of the galaxies is very, very similar. So that tells you that the universe is the same in all directions. But how do those galaxies that are 13 billion years old in one direction know about those galaxies that are 13 billion years in the other direction? The universe hasn't existed long enough for the light to travel from one to the other. Okay, they haven't been close enough to sort of mix and mingle and homogenize and become the same. So this is where the concept of inflation comes in, that at some point in the early universe, the universe was able to mix and homogenize, and then there's this period of inflation, which led to this rapid expansion. So I'm not doing a very good job of this, but there is no center to the universe. No matter where you were, you can only see out to your horizon. And in this case, you can only see out to about 13 billion light years, because while the universe existed and exists further out from that, there's nothing luminous there. The stars haven't formed in the galaxy yet that are going to be bright enough for us to detect. And so there's nothing to see.
Carolyn wanted to add something to my question. I've pondered on this so many times, and I love the explanations. I go away, I get incrementally closer to the beginnings of an understanding of it. But Carolyn,
I can't get my head around this. So what is the universe expanding into?
It's not expanding into anything. And this is the thing. It's not like there's a great big empty space into which the universe is expanding. It's not like a firework going off in a big empty concert hall and there's bits of debris flying into an existing concert hall. Space is expanding.
I always pictured it like the surface of a
I can't
balloon.
get my head around this.
If you take the surface of a balloon, put 2 dots on it and measure the distance between them, when it's uninflated, it'll be what, an inch? Now you blow it up. Now measure the distance between those 2 dots and it'll be several inches.
I know all this, Kevin. I know all I still can't get my head around what is happening at the edge.
Well, there is no edge.
Oh, there you go. You see, that's the problem.
You see, now this is where we as human beings, we're used to a three-dimensional world, okay, and we think in three dimensions. But to use Kevin's great analogy, a balloon doesn't have an age. No matter if you were an ant crawling along on the surface of that balloon, you could walk forever and you'll never come to an age that you're going to fall off. Now that's a two-dimensional analogy because an ant, to all intents and purposes, thinks in two dimensions. It can move left and right. It can't really go up and down on that surface. Now that's very difficult for us to wrap our heads around in terms of the universe, but it's the same sort of analogy, that the space between objects is increasing over time, but there is no age. You could travel forever in a particular direction. You're never going to come to an age. In much the same way as you could travel forever on the surface of a sphere, and you're not going to come to an age.
But you go back to where you started.
You would eventually come back to where you started, yeah.
I love this, and it all started as a singularity.
Well, the balloon was uninflated at some point, and the balloon keeps expanding and expanding and expanding, and you just keep on walking, trying to get from one dot, which started with another dot, an inch away, and you never get to there.
Yeah, but the balloon still has a center. I still can't get my head around.
That's thinking about the balloon as a three-dimensional object.
I still can't
think about
we say it started from a singularity. Well, presumably that is the center, then, is it not?
Not the third center of the balloon in the 3 dimensions.
I can't get my head around. There's no center where it all started from.
So
I can't understand the explanation that there is no center. I appreciate we can't identify where the center is, but I can't appreciate the fact that there is no center. See, it all came from one point at some being, and expanded from that point.
The jump that you need to make is into that 4th dimension of time, which again, that's why in the basic physics models they start you in two-dimensional planes, basically a surface like the surface of a balloon, and then they add the 3rd dimension, then they add the 4th dimension of time, and that's where it's one of those things that you sort of have to just. There's a point at which you have to jump over the fence and go, actually, I'll just accept that, because you can. There's no center in the sense of a 3-dimensional object, because it's actually in 4 dimensions.
Wow. Okay.
Your mind explodes, and even the big brains like Einstein struggled with some of this stuff.
Kevin, you're saying the universe is 4-dimensional.
Of course it is. It's measured over space-time. 3 dimensions of left, right, up, down, forward, backwards, and then measured over time. See, and that's where when you start to read some of the really weird books like Hawking's papers and stuff like that, they start getting into these weird positions, and you just think that's way beyond my scope.
Beyond mine.
Just leave me in the 4 dimensions. I'm okay with that. I can just about cope with that.
So do we think has Hubble seen as far as there is to see?
The CMB is probably as far back, isn't it, William?
Yeah, the cosmic microwave background. So what that is when the Big Bang went off, okay, the universe consisted essentially of plasma. So it was essentially a soup of subatomic particles, okay, a bit like maybe the inside of a fluorescent tube. If you were there and you had a good enough spacesuit that you didn't get instantly vaporized or killed by radiation, okay, if you looked out, you'd just see essentially a white glow. Okay. Now, as the universe expanded, it cooled down, and there came a point where it was cool enough where protons could capture electrons and form neutral hydrogen atoms. Okay, and that's what's called essentially, it's called the last scattering surface. At that point, the universe became transparent, and photons were able to travel large distances in straight lines without getting absorbed and re-emitted. Okay, and we see that today in the cosmic microwave background. Now, because the universe has expanded, those photons of visible light have been stretched in wavelength, okay? And they're not visible photons anymore. They're not infrared. They've been stretched so long that they now appear in the microwave part of the spectrum, and you have to use radio equipment as opposed to optical telescopes to see it. And no matter where you point your radio telescope in the sky, you get this this background cosmic microwave response. And Panzas and Wilson back in the 60s, you know, got the Nobel Prize for discovering this. And that's the last remnant of the Big Bang that we can see. And the furthest back we can see, sorry, it's furthest back, the earliest time we can see, and that's from about 300,000 years after the Big Bang. So no stars had formed at that stage. It's just when neutral hydrogen first became as possible for neutral hydrogen to first exist. And the other thing that's you know, maybe worth mentioning here, while we got the time, is, you know, I mentioned about, you know, the further away a galaxy is, the faster does the seeding from us. Okay, this is the red shift that we talk about. There comes a point where that red shift is faster than the speed of light. Okay, that galaxy is receding from us. Sorry, not receding from us. I should say that the distance between us and that distant galaxy is expanding so quickly that that speed exceeds the speed of light. The galaxy is not moving through space faster than the speed of light. It's the space between us and that galaxy is expanding at faster than the speed of light. Okay, remember Hubble's constant is about 73 kilometers per second per megaparsec. A parsec is 3.26 light years. Okay, so a megaparsec is 3.2 million light years. So if you measure a block of space at 3.2 kilometers across, and look at it 1 second later, that distance will have increased by another 73 kilometers. Look at it another second later, it will have increased by another 73 kilometers. If you're looking across a big enough chunk of space, that rate of expansion exceeds the speed of light. And the consequence of that is that there may be galaxies out at that distance, we could never see them because the light will never reach us. Because even though the light's coming towards us at the speed of light, the distance between us and that galaxy is expanding faster than the speed of light. So this is what people talk about, the observable universe. There comes a distance at which there might be stuff out there, we are never going to be able to detect it. And here's one of the more interesting issues around that. You know, we traditionally think of the Big Bang, and again, when I was younger, we talked about the Big Bang, and everyone assumed that, okay, you got all this mutual gravitation, all this stuff in the universe, okay? It might have expanded very quickly to start off with, but it should be slowing down because the gravity of everything should be pulling it back towards itself. And maybe the universe is going to end in a big crunch where it stops expanding and starts collapsing in on itself. And maybe there'll be another Big Bang, and it'll just be a cyclic thing, it'll keep on going. And that was a very widespread assumption up until about 1997, when there was some pretty shocking results came in, again, using data from the Hubble Space Telescope. And what astronomers were doing was looking to see if the Hubble constant was changing with time. And the way they were doing that were comparing the rate of expansion of the universe nearby with relatively nearby galaxies and comparing it with more distant galaxies. And the expectation was that we should see the universe slowing down. And what they found was quite the opposite. There was two competing teams of astronomers, and when the results came in, they thought, we must have messed up on our calculations here. So they went through them again, couldn't find anything. Eventually, they got in touch with each other and said, we're getting this weird result. What do your results show? Another guy said, yeah, ours are a bit weird too. What are yours like? And I think they eventually published, made a joint publication. The rate of expansion of the universe is not slowing down, it is accelerating. Okay, so this assumption that the mutual gravitation of all the stuff in the universe was going to slow down the expansion and bring it back towards a big crunch, that's gone away with now. There's something that's driving and accelerating the expansion of the universe. And this is what's known as dark energy. It's called dark because we have no idea what it is, and we've been trying to figure that out for the best part of 25 years, and we still don't know. And there's no really solid, good theoretical models that we can use to design an experiment to try and figure out whether our hypothesis is correct or not. So it's a genuine mystery as to what's driving this accelerating expansion of the universe. So the consequence of that is, if you're an astronomer millions or billions of years from now, with an accelerating expansion of the universe, you're going to start seeing less and less. Things are going to be disappearing over that horizon, over that observable universe horizon. And the universe is, and in the meantime, the universe is getting bigger, things are getting further away. So there's going to be less and less to see in the night sky. So it's ultimately far enough in the future, going to be pretty depressing. There's going to be very little out there to observe.
William, can I ask? I think Andy wanted to ask you a question. Andy Hewitt.
Mm-hmm. Go ahead.
Yeah, it's fascinating topic. Obviously, just bringing things a little bit closer back to home. I was quite alarmed at the rate of the moon's movement away from us, and wondered if anybody else was alarmed by that. And I wondered at what point in the future, when that will be, that the moon is distant from us, that there's a significance to us here on Earth, if that makes any sense.
The gravitational impact of the moon moving
that kind of thing
out.
Yeah,
absolutely. Okay, so
we'll be long dead.
Well, I imagine that, but I just wondered what that point in the future will be.
Okay, so there's a few things, again, really good science here. So thanks for that question. So obviously the moon raises tides on the Earth. Okay, that's where we get high tide and low tide, things like that. And it's just at a position in terms of Earth-Moon distance where it's just covers the disk of the sun, so we get to enjoy total solar eclipses and see the solar corona. At some point in the future, we're not going to see that anymore. We'll only have annular solar eclipses, where it won't cover the full disk of the sun anymore, because it's going to be further away from the Earth, and its angular size is going to be smaller. But it's not going to recede forever and ever and ever. There's going to come a point where it stops receding, and the reason for that is that the reason it's moving away from us is due to a transfer. I'm going to use a technical term here: transfer of angular momentum. So let me explain what's going on. If the Earth did not rotate, okay, that bulge of seawater that forms a high tide would always point directly towards the moon. Okay. But the Earth does rotate, and friction with the seabed sort of drags that bulge slightly ahead of the moon. So if you were to draw a line from the center of the Earth to the top of that bulge, it doesn't really point at the moon. It points a little bit ahead of the moon, in the direction that the Earth's rotating. And so what then happens is that because you've got a large, massive object, this bulge of seawater, okay, pointing out into space. Now it's only a few meters, so nothing to get alarmed about. It's a few meters pointing up towards the moon, and it's sort of pointing ahead of the moon. It actually has an effect of tugging on the moon and accelerating the moon in its orbit. Okay, trying to make the moon go faster. And it's being successful. It's actually making the moon, transferring angular momentum from the Earth to the moon. So the moon is getting faster in its orbit, which has the effect of raising the height of the moon's orbit. But you don't get something for nothing. The other effect is that it's actually slowing down the Earth's rotational rate. Okay, so if you look back at ancient, fossil records from ancient coral reef from, hundreds, if not billions of years ago, probably hundreds of millions of years ago, rather, because billions of years ago we didn't have life. There are certain corals which have a daily growth ring pattern, much like we have an annual growth ring pattern on trees. Okay, And overlaid that daily glow-sling pattern, you see seasonal variations. And from that, we can see clear evidence that the Earth did not used to have 365 days per year. It used to have over 400 days per year because the Earth was rotating faster. And over the intervening period, the Earth has slowed down in its rotation rate and raised the moon's orbit. So ultimately, at some point in the future, what's going to happen is the Earth's rotation rate will have slowed down sufficiently that they will become tidally locked. So I'm sure you're familiar with the fact that the moon always presents the same face to the Earth. And that's because its rotation rate is the same as its orbital period. A similar thing will happen with the Earth. The Earth will keep the same face pointing at the moon, okay? Because it will have slowed down sufficiently. And at that point in time, there's no more accelerating force that's raising the moon's orbit. The moon will stop moving away from the Earth because you don't have that tidal bulge pointing slightly ahead of the Earth-Moon line. They'll all be in a straight line. Now, that's billions of years in the future, and not only will we be dead and buried at that point, but the sun will probably have reached the end of its life as well, expanded up, and potentially have swallowed the Earth and the moon. Or if it hasn't, it's certainly caused significant environmental damage.
That's good to know. Thanks.
But Andy, don't hang around for too long. another 50 or 60 years, and then call it a day.
Yeah. No, it's fascinating. Thanks.
Yep. There's some really good physics in there, which you can look into, or.
I understood pretty much everything that you said there, which is not something I can say for the rest of the talk or the information that you've given, because it is mind blowing, as everybody has said. But no, that's really, really good. Thank you.
Okay, no problem.
Does anyone else want to ask a question of William?
And Andy, if there's something you want me to go over again, just to explain, you mentioned a few things you didn't understand. If we've got time, I can flick back a few slides and go over something again if you want.
I always enjoy these. Sorry, did someone ask a question? I thought I heard someone talking as I was.
I was about to say that I didn't quite get the when you had the boat at sea. And it was 4 miles away, and you had people on one side of the deck and on the near side of the deck, and people on the far side of the deck. I didn't quite follow on what the significance of that was with the rest of the thing that you were saying at the time, but that might just have been me and my stupidity.
Essentially, what I'm saying here is that I use this analogy because let's say the ship's exactly 4 miles away. Some people are a little bit less than that because they're on this side of the deck. Some people are a little bit more than that because of the far side of the deck. Okay, but in general, you'd say they're 4 miles away. And if you look at the large, small Magellanic Clouds, if you were to spot a Cepheid variable, it doesn't really matter whether that Cepheid variable is on this side of the nebula or the far side of the nebula.
Oh, okay.
Generally speaking, they're roughly the same distance.
Right. So it was just a relativity type analogy.
Yeah, a relative distance standpoint. You'd sort of say it doesn't really matter if you're trying to figure out the distance to the small and large Magellanic Clouds. If you're looking at a Cepheid variable, it doesn't really matter whether that Cepheid variable is on this side of the nebula or the far side. Okay, it's good enough. It's good enough to figure out roughly how far away the nebula is.
Thank you.
Yeah, sorry if that wasn't clear there earlier.
No, I probably just missed it because my brains were being fried.
Okay.
I think we're getting close to our 9 o'clock time. Does anyone else have any burning questions, new subjects to raise, or do we start to wrap the evening up? I'll take that as no further questions. William, I've enjoyed this talk as much as I've enjoyed all of your talks, and I find this talk.
I don't know if that's a good thing or not, Phil.
It was sorry. I was trying to say a compliment. I have enjoyed enormously all of your talks, and I was going to go on to say that I find that the talk and then we get two experiences for the price of one evening, because we have the talk. I do enjoy the chat afterwards.
Yep.
And I always come away from talks like this realizing that how little I know, and I've written a great long list of things to find out about, which I will one day find the time. And the four-dimensional nature of the universe and understanding space-time, and to marvel at the people who worked out the diameter of the Earth and the distance to the moon, and it just, your talk has covered a lot of ground, a lot of history, a lot of facts, and it's provoked a lot of conversation about cosmology and many other subjects, and I've enjoyed it enormously. So I've enjoyed this enormously. I've enjoyed all of your talks enormously, to remove any doubt in your mind. And I would like to say, on behalf of West Didsbury Astronomical Society, a very big thank you, and a thank you to the attendants, everyone who's listened in, and to those who've raised questions, for a very, very enjoyable evening.
Yep, thank you very much.
And I